Welcome to the penultimate session here at Spark Summit Europe. There's only one more, so you've made it this far. And hopefully we can teach you something over the next 40 minutes. So Bogdan and I are going to discuss some of the challenges we've faced at Databricks in trying to build an analytics platform at scale in the cloud. And so it's a work in progress, right? There's a lot of problems to solve here. So maybe we're viewing this as the first part of a series of talks over the next couple summits. So we're going to be talking about two major challenges that we've encountered so far and our solutions for them. Oh, that jumped way forward. OK, so who are we? I'm Chris. I'm an engineer at Databricks from our San Francisco office. Bogdan works locally here in Amsterdam, just down the road. So this talk has been a cross-geo effort, collaborating early morning for me and afternoon for him. So hopefully you enjoy. So data analytics. What does a day in the life of a company doing data analytics look like? And so we're going to talk about two personas here. Bob, the data analyst, and Alice, the admin. And they kind of have competing goals here. So Bob wants to be able to use whichever BI tool he's comfortable with. He wants to run interactive queries, and he wants those queries to execute efficiently. Alice, she wants to maintain a stable system for Bob, but maybe reduce cost, minimize cost. She doesn't want to be spending a whole lot of money to run these workloads. And so you could think in a simplified case, Alice goes out to the store, buys some machines, plugs them in, runs them between 9 and 5, and Bob gets to run his queries. But that doesn't really scale, because the reality is that there's one Alice, but there are many Bobs. And more Bobs show up at lunchtime to run more queries, or after lunch, I guess. And then maybe in the afternoon, some of them disappear. And we don't need to spend as much as we did at the height of the day when there are lots of queries going on. And so Alice needs to be able to manage that load and wants to simplify her life. So with this talk, we're going to talk a bit about Bob, about the tools and the connectors he wants to use to be able to talk to Spark, and then a bit about resource management and how we're making Alice's life easier at Databricks. So with that, I'll hand it over to Bogdan.
Thanks, Chris. So I think many people in the room here share a common goal, that is unifying big data analytics. And one such workload is the BI workload. And by BI, we mean business intelligence workloads. These are quite interesting workloads because they are typically generated by an external tool, like Tableau here. You may also use Power BI or Looker. And the image that comes in mind is basically a business analyst that is in front of a dashboard. And it starts interactively play with the dashboard in order to connect to a data source and retrieve and visualize the data that it's looking for. So in order to understand how such a workload performs on a runtime system like Databricks, we set up like an end-to-end pipeline here, starting from the external tool, going through some intermediate layers until it reaches Databricks. Now, what is interesting here, and I'd like to point out, is that a query that is generated by Tableau spends a quite significant part of its lifetime before it's reaching the actual cluster, before actually it can start running. So let's take a closer look of what's happening. We collected logs from all these intermediate layers, and we tried to visualize an event flow to kind of define a query lifetime. Looking at Tableau, every operation that Tableau performs, it's happening within the boundaries of a session. And this session is delimited by construct and destruct events. Before starting to run the actual query, Tableau needs to retrieve and to figure out what the schemas of the data tables involved in the computations are. So for that, it's using a JDBC ODBC driver like Simba in order to retrieve different bits of information, based on which it can generate and construct the actual query. After that, it executes the query. When the query is done, then we can fetch the result. And we can see that fetching this result involves like multiple smaller queries that go back to Tableau. And Tableau renders basically the data, and you can actually visualize your dashboard. So this is what happens like conceptually, but let's take an actual example of what happens behind the scenes. So here we visualize a number of things. The very first column shows like the event flow on the initial connection to the data source. So when you're logging into Tableau and you're connecting to the data source, and we see that Tableau here also sends a bunch of metadata operations in order to figure out information about the data source. And then we have a TPCDS query, the execution of a TPCDS query on a cold run, followed by subsequent worm runs. Now, on the code run, we see that the execution of the query with green, actually, it's in the range of tens of seconds. And the reason for that is because on the first run, the data has to be fetched from S3, so it's a cold execution. But however, what's interesting here, and I'd like to point out, is that these metadata operations, they're not zero, right? So there is some time spent on figuring out these bits of information. What is even more intriguing is that when we move to the worm runs, the runtime of the query significantly improves because of our delta cache, which doesn't require going again to S3. And these metadata queries actually start to dominate the turnaround time. So we have a problem here. And if you look at individual metadata queries, they're actually not quite expensive. If you zoom into a particular one, they are like in the order of tens of milliseconds, even milliseconds. But there are some gaps in between them. So there is some overhead, and we'd like to figure out where this overhead is coming from. Now, one simple way in which we can optimize and reduce latency is basically to strip the intermediate layers. But this is something that Databricks cannot actually do, because we are not only interested in providing good performance for the customers, but we also want to provide them a secure and safe environment. So this is like a high-level representation of a simplistic architecture that we have. And we distinguish here like a control plane and a data plane. And imagine like from the control plane, we are managing the deployment of the clusters, starting up, acquiring virtual machines from the cloud providers, making the authentication for different users, providing echo checks, and all these mechanisms that are happening in the control plane. And the data plane is actually where the user is running their workflows. They have control over the clusters and over their data sets. So what can we do? We cannot remove these layers, but what can we actually do? Fortunately, Tableau released recently a connector SDK, and that allows partners like Databricks to build their own customized connector and plug that into the distribution of Tableau. So a connector in Tableau, basically, it's a set of files in which you can control the UI elements that the user can provide input in order to build the connection string that goes over ODBC or JDBC. And you can also do a bunch of networking customizations and also SQL dialect changes in order to control the quality of the queries that get generated by Tableau. OK, so currently Tableau has a Spark SQL connector. And if you connect from Tableau, you see something like this. Some of these elements are not necessary, so we really wanted to provide a simplified version of this. So with the connector SDK, we could control that. We simplified this dialog box, and we have something that is easier to discover and also easier to makes it easier for the client to connect just by specifying the credentials and like cluster path. Now, besides having this simplified version, one of the main reasons, if not the main reasons, for which we started building this connector was to improve the correctness and the quality of the queries that get generated. Because the yardstick for having a connector in Tableau is this TDVT benchmarking suite, which is a correctness suite consists of about 900 tests. And we found out from our analysis, we found that the Spark SQL, the default connector that it's currently exists, has a bunch of problems, so about 200 tests were failing. And luckily, with this SDK, we made the appropriate changes, and we improved the dialect because it was mostly inheriting from the Hive dialect, and it was a clear mismatch between the tests that were expecting certain features in the dialect that Hive didn't support. So one such example is, for instance, the right split function, which we could immediately fix using a template in which we are providing a formula for running that computation. In this case, we are using the Spark left split function and applied to the reverse input string and input separator. Now, there are a bunch of other inconsistencies that we found and we could fix in a similar manner as in this example. And finally, we achieved like a 100% compliance with this benchmarking suite. Yeah, I don't know, this is not working probably anymore. Okay. Anyway, so coming back to the actual metadata queries and the latency, we analyzed how Simba retrieves the results from the thrift server. And it turns out that after we submit the query, there are these polling intervals which are set by default to 100 milliseconds. And here's the problem. 100 milliseconds may not sound much, but actually the metadata queries are like tens or even 1 millisecond. So there's clearly a gap that we are waiting for because the very first poll goes after 100 milliseconds. So by simply reducing that to just 1 millisecond, actually the latency on a simple benchmark in which we are just connecting to the data source was basically cut in half. Digging a bit deeper into the metadata queries, these are expensive, so we try to see if there's a way in order to minimize the impact of them. And it turns out that Tableau actually sends a sequence of them for each table that is referenced in the query. So if we take, for example, TPCDS query 3, if you are familiar with it, if not, it's basically a join of 3 tables. For each of these tables, Tableau sends 4 metadata queries. So in total, we get like roughly 12 metadata queries. And considering that thrift is quite a chatty protocol, and basically a Wireshark analysis showed us that there are about 6 round trips per each such metadata query, you get easily to like dozens of round trips per the execution of a single query. And also by customizing this connector, we could actually reduce the number of these queries to just a single one. So we are retrieving all the metadata query in just one go, and reducing basically by a factor of 4 the number of round trips. And on one of our benchmarks, this has shown to be very effective. Yeah, so here I'm showing some results in which we are setting up Tableau on one region and Databricks in another region. And the closer these regions are, basically, the 2 connectors are not that far apart, with a clear improvement on the Databricks connector. And while we're moving these regions farther apart, so for instance, we're going from Europe to US, this gap becomes larger and larger. So far, we have followed the lifetime of a query from an external tool up to the entry point in our Databricks runtime, up to the thrift server. And now Chris will continue to tell you and explain how our cloud infrastructure works and what type of mechanisms we have there to provision our usage.
Thank you. Yeah, so Bogdan was talking a bit about Bob's life, talking about shaving milliseconds and round trips off of his queries, which is great for his response time. I'm going to talk a bit more about Alice's life and how can she manage the cost of her cloud infrastructure while not totally ruining all the work that Bogdan has done to reduce the latency of Bob's queries. And so throughout this portion of the talk, we're going to kind of relive this experiment that I set up on multiple different Databricks configurations. And so what this experiment is running a TP-CDS query every 20 minutes. So you could think of it as like a dashboard refresh in some, from some BI tool. Obviously, it's a little bit simplified. There's only one query showing up every 20 minutes. And so it doesn't really demonstrate the issue where you have multiple Bobs coming in and out. But it can at least, as a pet example, to show how to manage cost of the cluster. And you can extrapolate out to more use cases with more Bobs. You can think of the query coming in as a flurry of activity for multiple users if you want. So anyways, this first graph is sort of like, I kind of think of like on-prem in the cloud. The easiest thing Alice could think to do would just be create some cluster, leave it on, and eat the cost. And so in this case, what we see here is the initial latency to start a cluster is some 200 seconds. And then the first execution of the query runs. That actually loads, pre-warms things like the Delta cache. And then we get this subsequent consistent tick for each every 20 minutes when the query is submitted. And that gives us kind of a roughly consistent execution time of around 315 seconds. And this we're going to use as our baseline for future comparisons. And the cost of running this cluster per hour is about $15, just to use real numbers. So that's great for Bob. He doesn't have to worry about the latency of his queries. The cluster's already running. He can just quickly attach to Spark and get going. It's not necessarily great for Alice, who might lose her job if she's spending too much money. And so if we look at the opposite, sort of a cost-optimized model, where we shut down the clusters when we see idle periods, this is sort of what we get. So each red line is a cluster start, and that's when this dashboard refresh is starting, when I want to get my result, right? But in each case, there's about 200 or so seconds where we're waiting for the cluster to start. And I'll talk a little bit about what's going on there in the next slides. But as a result, the execution time from query submitted to result goes up by almost 5 minutes. Because each time we have to download the data, there's no warm cache. And so it's much worse for Bob. But Alice saves some money, almost half the cost. And so if we compare these two runs, click, OK. We can see that this ephemeral cluster that starts every time the query comes in is half the cost in red on the right, but it's 2x the execution time for each of the queries. So there's a trade-off here. And again, when we see these charts throughout, the fixed size cluster, fixed cost per hour is going to be the baseline. So I talked a bit about why that 200 seconds to start this ephemeral cluster, right? That eats into the execution time for Bob. So why does it take 200 seconds or so to start a cluster in the cloud? So here's kind of a simplified version of the Databricks platform. So a cluster create request will hit our cluster manager, at which point it's going to go talk to one of the clouds we use to provision instances. Now, the cloud provider is doing a ton of work to go find actual physical cores to run these instances or VMs on. And so there's some amount of time to wait until you can find a free slot for that. That can take 25 to 30 seconds. And then after that, you actually have to wait for the VM to warm up and be SSHable and reachable, after which we can then start installing our sort of daemon sets on the node so we can monitor the activity that's going on and actually deploy workloads. And so that initial process of allocate the VM and set it up takes almost a minute. And then once we're at that point, we can actually launch a container and start Spark. You'd think, OK, 30 seconds to launch a container. That involves downloading DBR, which is about a 5 GB image, the Databricks runtime, our version of Spark. And then initting Spark takes 15 seconds. A lot of that is just starting JVMs. JVMs don't necessarily start quickly. There's a bunch of papers about how to do that if you've cached them, et cetera. We're working towards those solutions, but maybe next year's summit. So this is sort of the basic picture. And let's look at some production numbers, right? So this is over the last month, median start times for each of these sections, up to 55 seconds. That's where I'm getting these numbers to allocate the resources. But if you look at the median for the actual cluster starts, it's almost 2.5 minutes. So as much as it's cost optimized, it's not necessarily cheap to just spin up a cluster in the cloud. So what could we do to balance between these two, right? I don't want the cluster, or maybe I want the cluster up and running, but I don't want it to stay at this fixed cost with 20 nodes, or at least in this setup, at all times. So hey, why don't we auto-scale the cluster? And so in this case, you can have your cluster run with a couple nodes, but then when more Bobs show up and need resources, we will dynamically go allocate more VMs from the cloud and scale up. And so in this case, on the Databricks platform, sort of like the dynamic allocator within Spark, the cluster manager is listening to the DAG scheduler's information about active pending tasks, and it's responding to those, saying, OK, my cluster is under provisioned, I should go add nodes. And so it reaches out to the cloud provider. Sort of the same process that we saw in starting a cluster can happen dynamically to upscale a cluster. And then downscaling. Downscaling is sort of the reverse. We get scheduler info when we see that the cluster is over-provisioned. We can take away VMs to save cost. But a naive approach to autoscaling really would just look at active and pending tasks, and it wouldn't be aware of where those tasks, the active tasks, are running. Because as you probably know, Spark will allocate task slots for a stage to some executors, maybe not others. And then that stage might leave around shuffle files, and so that we need in subsequent stages. And we can't really be sure where all these things are. So a naive approach for autoscaling would be give it a big, long time window to idle out. And then if and when it's idle, start taking away nodes. And this version of downscaling is not aggressive at all. It takes away one node, waits 10 minutes, takes away 2 nodes, waits 10 minutes, 4 nodes, et cetera. And so in this pet experiment, we actually really don't downscale at all because of our arrival period of 20 minutes. In that time, we can only downscale by 1 node. So this isn't super great. It's pretty good for Bob, but not for Alice, right? So the execution time is only 4 seconds slower on average for Bob, but the cost is almost the same as this fixed-size cluster. So that's not super great. So let's try to optimize this a bit better. And so in the optimized autoscaling that Databricks offers, we actually are aware of what Spark is doing. And so we look at which executors are running active tasks, where the active shuffle files are, so we can actually more aggressively downscale a cluster while it's still running subsequent stages. And this can save money, clearly. So in this case, the green trend line is the actual number of executors that are running, and that's basically 1 for 1 with the number of VMs that are actually provisioned for this cluster. And so as soon as that query is over, we know and we're done, and we can aggressively downscale safely that we're not going to kill some active task or delete some active shuffle file. And this saves a ton of cost. Now, if we look at the upscaling trend here, we've downscaled, we've gotten rid of the VMs. So now when the query comes in, well, we have to go get them, right? And so we're not going to just go get all 20 to start. We might hedge and say, let's go get 2 and then 8, and then reach our maximum of 20. But each one of those is 2.5 minutes or so, right? Because we've had some more nodes we want to make. We're not sure if that's enough or not, so we'll wait. OK, it's not enough. Let's add more. But because each of those steps takes 2.5 minutes, it's pretty slow to upscale. So Bob's execution time has actually gotten worse. It's now 700 seconds, even though the cost is actually pretty good for Alice. So how do we solve this problem? Given that it takes so long to acquire instances from the cloud, a Databricks product we've built, and it's actually GAing next week or something, is instance pools. Let's get, oh, OK, well, missed a slide. This is the comparison, but we'll skip that. OK, so yeah, instance pools. It's basically a managed cache of VMs that you can keep around associated with your cloud account that Databricks can take advantage of to reduce that scale-up latency. And so in this case, when you want to upscale, the cluster manager decides, based on the scheduler info, that it needs more nodes. Rather than reaching directly to the cloud, it asks the pool manager to allocate an instance. The pool manager is smart, and in the background, it's got some instances ready to go. And thus, that upscaling step, we've taken the 55 seconds and made it milliseconds, because we have that VM already ready to go. And then we take the time to launch a container and start Spark. Downscaling works sort of the same way. When we decide the cluster is over-provisioned, we'll just return the instance back to the pool. And another advantage of pools here is that when those instances get idle in the pool, they can actually be used by another cluster. Right? They're not just one-for-one with this cluster. You can share them across workloads. If you have 2 different clusters for 2 different business units doing BI analysis where you don't want them to interrupt each other, right? So this pool can be amortized. The cost of the pool can be amortized across multiple workloads. So let's see what our experiment looks like. OK, well, yeah. So more production data. So these are the median start times and upscaling times of clusters using pools, right? So we've totally eliminated that 55 seconds, and it's almost 3 times faster to start or upscale a cluster from the pool rather than straight from the cloud. All right, so here's our experiment again. In this case, we have a fixed size pool. So this is fixed sort of cloud infrastructure cost. So the variable of cost here is going to be the Databricks cost on top of that. So any sort of managed service that's running Spark for you in the cloud, EMR has a similar pricing model where when you're actually using the cluster, you're going to pay. So that's kind of the variability in the cost between this and a completely fixed size cluster. And we can see that the scale-up time, we've sort of reduced that latency because the instances are coming out of the pool. And so rather than it taking 200 seconds, it's taking about 60 seconds to do the 2 scale-up steps. And then we aggressively downscale to save cost, and then scale back up when the next query arrives. Now, the execution time is better. It's not really at that 300 mark, because we do have to wait the extra 60 seconds to scale up to actually achieve maximum utilization of the 20-node cluster. But maybe it's a good balance between Alice and Bob. And so the last experiment I ran is to dynamically change the size of the pool. So one of the things you can do with an instance pool is set the minimum idle nodes that you want. So in this case, I said I always want 5 idle nodes, no matter what. And then as a cluster needs nodes, it'll pull from that pool of 5 idle nodes. And in the background, we'll add more idle nodes to make sure we keep that minimum. And then when instances are returned to the pool, any node that's idle beyond that minimum of 5 will be returned to the cloud after 10 minutes. So this experiment didn't actually turn out so great, given the 20-minute interval between queries, because you can see here in this gap that we actually ran this query fast enough that there was a 10-minute gap here where we lost instances and scaled all the way down to 5. Right? So 5 nodes only helps us with the initial start. It doesn't help us get up to this hurdle. So it's actually fairly slow and wasn't better than, say, just the fixed pool. And so this is something that Alice would have to tune to say, OK, here's the patterns of workloads from my many Bobs. And maybe these settings are better on the pool than others. But this is just an example that it takes some tuning to get it right. And so if we compare all these workloads, again, using that fixed size cluster as our base, we see that we can, sort of the best case for execution time is the naive autoscaling or the fixed cluster. The best cases for cost are still the ephemeral cluster where we shut it down all the time. But we see like this orange is maybe a happy medium where it's not too bad for Bob. It's 1.2x, but Alice has saved some cost. And that's the case where you have a fixed size pool in the background, but then using aggressive or optimized autoscaling to scale your cluster up and down. Anyways, so that kind of wraps up the Alice part of the talk of how do you look at cost versus the execution time for BI workloads. And so some of the things that we've sort of learned in this process is that it's not just one piece of software or one piece of infrastructure that's tying your BI stack together, right? We've got Spark at the core. That's actually the execution engine. But we have the cloud providing the resources. Databricks as a platform managing those resources, doing things like security and ACL checks. And then you have the Tableaus of the world, the dashboards and all that are actually the user-friendly tools you want. And so when you glue all those things together, there are challenges. And so this is what we've sort of learned throughout this portion of the talk, is that integrating them is very powerful, but you need to know what you're doing. There are inefficiencies along the way. And so that's some of the stuff that Databricks is looking at, is to make sure that we are being optimal and removing those inefficiencies, and then sort of educating you about how you manage your clusters and the cost in the cloud. So, questions?
Thank you, Chris, and thank you, Bogdan. That was really great, and I think that really helps, and that's what we really see also, optimizing costs and the efficiency of the cloud. So are there any questions that you might have? Oh, we have one question over there. Great.
Since we have, in Databricks, we have auto-scaling, right? So dynamically, that based on the load, the cluster will be make it up, make it down. So now the pool manager, I believe that it's recently introduced the pool manager. So what is the difference between the pool manager and auto-scaling?
So repeat the question. The difference between the pool manager's scaling and like the cluster auto-scaling? Is that the question?
Yeah, so what is the difference? Because already we have the auto-scaling, like the node, the minimum I can set to configure such a way that minimum node 2 node, maximum 8 node, right? Mm-hmm. So when you oversee runtime, so automatically based on the load, it will increase 4, 5 node. If the load is less, automatically get reduced to 2 node. So where is the come to picture pool manager? That's my questions.
Yeah, so right, so the cluster auto-scaling, right, that's based on Spark scheduler information, right? The pool doesn't really have that intelligence yet. Right, because this pool can be shared by multiple clusters, okay. Right? So, kind of the vision there is to look at workloads, anticipate workloads, to know how to backfill the pool to make sure that it's ready to go when the workload starts. One of the challenges that we have with the Databricks platform is that we run the control plane in our cloud account, but the data plane where Spark runs is actually in the customer's account, and so we need to make sure that the customer has a way to manage that cost. So today with the pool, it's sort of a reactive over-provisioning where you set that min idle, that I always want 10 more instances available, right? And so if I consume any of those 10, say I consume 3 from my cluster, we're going to backfill 3 more as a result of reacting to that cluster allocating the resources, if that answers your question.
Okay. Thank you.
Okay.
We have another question here.
Hello, thank you for the talk. It was great. You made a comment about the pool manager can share resources among multiple clusters.
Yep.
What are your thoughts on having multiple analytics clusters? So, marketing team has their own cluster, and HR has their own clusters. Is that a good approach, or it should be one cluster at enterprise level?
That's a good question, yeah. So one of the things that we kind of have been looking at is the kind of the maximum concurrency that like one particular Spark driver can handle, right? And that's kind of the question you're getting at, is like, right, how many clusters do I need? And so, Bogdan's actually dove in a ton there. We don't have solutions or results to share yet, but I think that depends on your workload, right? So, given that there's just one driver tons of interactive queries, right, eventually it might have a bottleneck, right? Or if you're trying to collect a lot of results on that driver, drivers, it's it can happen, right? So I think it would be up to you to figure out, okay, what's maybe the security model between these two business divisions, right? And so to say I need to have separate like permissions on this cluster versus this cluster, right? And the pool, can serve as a background there with and maintain that security though, because we're not going to share. Each cluster is going to be containerized, right? So even if they're sharing the pool, you're not going to be able to jump out from some UDF that's running to attack another cluster that has a different security model. But it really depends on what your workload is. If you can fit it all in one cluster and that's okay with you with respect to security, that's maybe fine. Or you spread it across multiple clusters.
Thank you.
Thank you for that question. I think we have another one here.
Yeah. Hello. So I just wanted to ask, because you said it's GA this week. So if it's available already, or will be, the same way as auto-scaling was available in the cluster management tab on the Databricks, right?
So about the pools GA, is that the question?
The question is, how can I get this optimized auto-scaling
okay, yes.
up and running?
Got it. Yeah, the GA I was talking about is for the instance pools. That's public preview now, so anybody can use it. But with the optimized auto-scaling, it is included in the Azure Databricks premium tier. And then for AWS customers, it's on demand. I think you'd have to negotiate with, talk to your solutions architect or your point of contact on the sales side, and then we can enable it for you.
Okay, and the other question is, how do I get these executors graphs that you've shown?
Let's see. This is data that is we log every so often in the Spark driver to tell us, where how many active tasks, pending tasks, active executors, total executors, executors with shuffle files. That is in our logging pipeline, so not public. But something we are working on is sort of visualizations like this, right? So I can say, on the cluster page somewhere there should be a graph to say how well utilized is this cluster, right? And so you won't have to stream through raw numbers. We're working towards actually giving you a graph so you can see, if you're benefiting from auto scaling or et cetera, right? So that's coming. We're not there yet, but so hopefully you won't have to do anything.
All right, thank you.
Yeah.
Hi, thanks for the talk. I wanted to ask you, what are the differences and similarities between instance pools and the Databricks serverless?
The Databricks serverless, okay. So I think the serverless clusters, that's what they used to be called, are serverless pools. Now I think they're branded as high concurrency clusters. And so the purpose of those is if you have, so you're going to get better utilization, kind of to your question, if you have many people using the same cluster, as long as they don't exhaust its resources. And so the idea behind the high concurrency clusters is that I can have different users that don't necessarily trust each other run on the same cluster. And so on those high concurrency clusters, we don't let you run Scala, because that runs inside the JVM. And so if everybody's running Scala, they can look at each other's memory. And so we only enable Python R to run there, and we have process isolation. So each Python REPL that's running workloads has its own low-privileged user process, and we've sandboxed that in terms of a file system jail, restricted its IP communication access, right? And so that's when you're talking about a serverless cluster, trying to get many users to run securely on one Spark application. Pools are sort of separate from that, right? You can think of pools as a yarn cluster where you can run many Spark applications. I think that's maybe a mental model to think about. Pools more like yarn, whereas a serverless high concurrency cluster is just one Spark application.
All right, thank you.
Thank you for the questions. Are there any more questions? Some questions? Okay, cool, great. Maybe I have one, actually. Chris, so how can we actually help Alice maybe to anticipate in the future what it will cost upfront so that she can actually do some kind of like budgeting and things like that around, knowing the cost maybe upfront?
So the question is, how can Alice anticipate the costs?
Yeah.
Yeah, so I think when I talked about the graph that we would hopefully show on we're working towards showing on the clusters page, something else that has come up is how do I attribute cost to particular users, right, or teams, right? When you're almost looking at that cluster utilization level, like which queries or which workflows are driving up the cost for this cluster? Why is this cluster so expensive? Right, and that's something we're trying to build into the Databricks product as well. Clearly the next step there is to have some learning behavior on top of that, right? To say like, Alice, I recommend, you should tweak your cluster to look like this, or use pools here, right? As a learning engine. But that, is down the road. Once we kind of just give you the raw data, then we'll learn on top of it.
That
yeah,
sounds awesome.
interesting direction.
Cool. Thank you, Chris. And Bogdan, maybe to you,